Hey guys, so I wanted to go ahead and do a video on this HackerRank problem, the Java visitor pattern. I had trouble with it, and it had very little to do with coding. It was more of understanding certain aspects of the problem itself. So I wanted to provide more of a breakdown in video format, and hopefully that could help anyone get through this faster if they decide to take this challenge, right? So the problem's split up into two parts. Um, so this part one, well, overall, let's start at the beginning. You're working with a tree, right? Your tree can have a value, a color. For some reason, it has a depth, right? So, fine. So we're working with tree. We'll make a little simple one here. Boom, boom, boom. Root node at the top. So we have some value that could be whatever, some arbitrary number. 7, color could be red, and then depth is going to be 0 because you're at the root, right? Value here could be 3, color is green, your depth here is 1, right? Um, Whatever, I think you understand arbitrary values here. We could have another node here. And this node is node number one, the one at the root. So kind of just to clarify that. So what we're going to be implementing is some type of visitor. So each of these nodes are implementing or trees or whatever you want to call them um, are in, are implementing this accept method, right? And it takes some type of visitor kind of class. I think it's viz tree in the actual problem. Um, and this visitor class, the way the tree is implemented, will pass it on to its children. So basically, this visitor will visit every single node. And what the visitor can do is look at these properties and do some type of operation, collect some type of result that the visitor would hold. And at the end, that result could be called, So in this case, like summon leaves visitor, right? So that would collect the value, let's say, I'll collect the value here. I'm going to highlight it in green in this guy and in that guy. And I'll bring back the sum of that, you know. Uh, Product red nodes visitor. So it's going to look at the color. This one's green. No, we'll grab this one. Let's say this color was red here, right? And it does some type of special multiplication with using a modulus. That kind of tricked me up. So don't forget about this detail when you're doing this method. And fancy visitor, whatever. There's some criteria, some type of if statement that you're running through, and you're going to collect some type of value, or you're going to work with some type of value that you can return at the end, right? This part one isn't bad at all. This really went ahead, and I was done with this in 10 minutes, five. Really wasn't that bad. The real challenge is part two. So, and talk about working from something easy to something really difficult because you're kind of locked in with the tree that they've implemented here. Like part of the rules here is you're not touching lines 1 through 80, which have the tree already somewhat implemented there. Um, so cool. You're kind of understanding this open close principle concept a bit there. There's some code that you're not going to touch. Fine. I would say refactor the code and just make it easier because, hell, just to populate this tree is a pain in the butt. But um, the real challenge that I found was taking a minute to understand how to process the input format, especially this last part where It says each of the n minus 1 subsequent lines contain two space-separated integers, ui and vi, describing an edge between nodes, right? So I had to read that over and over again. But basically, what they're talking about this portion here. And let me actually take you through line by line how the input works. The first few lines are very simple to understand, and then this took me like a minute to get, right? So, first thing you're getting is how big your tree is, right? And that corresponds with the example that they give right here. So, 5 nodes in the tree, you see 5 nodes in the tree, right? And I'm just going to call each one of these a node. I know this one's supposed to be like, these are supposed to be tree leaves, and this is supposed to be a tree node. They're all nodes. It's not a big deal to me. And then this line corresponds with a value that's going into each of the nodes, right? So this respectively is node 1, 2, 3, node 4, and node 5, right? So that's what you have there, and you can see it there. This x1, this is representative of the first node. He has a value of 4. This second node has a value 7. Third node, 2, 5, corresponding to each of these. So cool. That's not too bad. And then the next line, again, it's nodes 1, 2, 3, 4, 5, and these are the colors. 0 is for red, 1 is for green. Again, not bad, right? Now, what this describes, if you're kind of just comparing this to the basic example given, you wouldn't be um, wrong to kind of just assume that maybe parents are on the left side and children are being described on the right side. But I almost wish the author would have taken the time to just reverse some of these, maybe have 1, 2, and 3, 1, because this almost implies directionality of the tree, which would make it not too bad to process. But no, you have to figure out the directionality because some of the other test cases, like this and this, what I'm highlighting right there, are the same. You know, node 3 is connected to node 1, right? So node 3 here is connected to node 1. And you could put that either way, you could flip it, right? Um, it becomes much more difficult to kind of build this tree also because it almost seems like it starts at the root and goes downhill. You'll find that with other test cases, these relationships are completely arbitrary, right? So let's actually walk through how to kind of visualize this. I want to actually visualize this for a second in Plant UML, this simple example, and we could do the same thing with one of the bigger test cases that have 100 nodes in it, right? So I don't know if you used Plant UML before, but it provides a very simple way to visualize this left to right direction. Because I'm a visual person, to visualize the tree in a sense. So if we specify the nodes here, I mean, it's trying to draw some type of class diagram. Let me see, did I typo something here? Oh, so I need to specify some type of relationship here. And let's start drawing this kind of short tree. If we extend out the length, it'll look a bit more like a tree here. I'll say that's better. So 1, and it has 2 children, you know, node 2 and node 3, and node 3 is related to 4 and 5. This diagram here is the same as the example that they give here, right? So, all right, what's the big deal? What's the point of all showing you all this? Okay, well, let's take a look at one of the bigger test cases. So this is one of the test cases: 100 nodes, 100 values, 100 colors, and then there are about 99 relationships to find. What you should notice, it kind of looks like it's in some type of order. You're thinking, okay, maybe parents on left side again, but no, not really, not at all. So let's go ahead and have this draw it out. And again, if you don't have like visual code, you could always kind of draw this out in Notepad++ first, drop it here, and this will actually generate it online without you having to um, install any software or anything like that. So let's get this drawn. And so now we kind of get kind of a quick reference that allows us to quickly imagine what this kind of looks like. We could see this relationship between 1 and 97. Here's node 1, here's node 97. And 97 has one child, which is 18. So if we look for 97, we'll find a relationship that it has 18, right? But you don't want to assume, you almost look at this and say, well, 18 is on the left, maybe it's a parent. No, there's no directionality specified. It's actually, if we're pointing towards the root node, the direction's kind of going this way, with 18 being the leaf of this whole concept. And imagine just parsing through this, trying to deserialize this. You process all of these guys, and maybe you want to say, okay, look, here's node number 2. All right. So let me find node number 2. Here we go. These are all node number 2s. Do they connect to 1 on this side at all? No, we don't see that. Maybe try it on the other side. Uh, Space there. And then we find no results at all here. 2's not on the right side at all. And you would almost think, I don't know, there's certain subtle imp, impressions that you might have or assumptions you might make. Is like, oh yeah, 2 is going to connect directly to 1. No, not at all. So if we wanted to say, look for 2, let's see, where's 2? Oh, here's 2. And how does it connect back to 1? Well, let's follow the path. So 2, and looks like 2 connects over 2. And it's difficult to even see here, but it looks like 2 connects over to node number 4, right? So we do see it here. 2 connects to node number 4, and then node number 4 connects to node 1, and we could see that plainly, right? But imagine when you're building out the tree at this point, so you have node 1 connecting to all these other nodes, right? And then you get to this part. Well, what you have is node 2 and node 4 connected. This almost looks more like a graph than a tree because it hasn't necessarily, well, at this point, it's integrated there. Let me see. Maybe I could find a better example of where you might not know, where you might have a relationship established and you don't know which one's connecting to the root node or if it's coming through another node back to the root. You, you're essentially establishing all these like random relationships first with who's neighbor, and then um, you have to go ahead and build it all together. Like for me, it just took me a minute to wrap my head around the concept. Well, let me see. Where are we at in the recording? Oh, 15 minutes in. All right. Well, I don't want to spend too much time on this. I'll make a second part talking about solutions, if anything, but I feel like that is just a better breakdown than what was kind of given in the description or kind of working with these guys here, right? So, anyway, hope this video helps someone.